Okay, am I audible? I think. Thank you, Manish, for introduction. I thank SPO Office, ISRO Headquarter, Dr. Praveen, Dr. Tej Pratham Das, and good afternoon to all the participants from various institutes and centers who have joined online. Today, we will discuss various aspects of scientific payloads for solar system explorations, in particular, but space exploration at large. And we'll cover these brief my presentation or discussion on two aspects. First, why these space exploration and how it is being done, why it is done. So these are the two major aspects which we need to understand. We'll understand how space exploration is being done with very good photographs and animation and examples. And space exploration, as all of us know, that it's a use of knowledge from the astronomy, astrophysics, planetary sciences, with including cutting edge space technology and hardware development and understanding and basic concepts from our scientific knowledge of various themes. And we'll begin this particular discussion. And first of and foremost is, what is the payload? Scientific payloads we are discussing. So what is the payload? Payload is nothing but an object or entity that is being carried out by an aircraft or by launch vehicle or rocket in the space. In this particular context I'm discussing, and here we'll be discussing about these scientific payloads, that means scientific instruments utilized for space exploration studies. And as you can see, the scientific payloads are designed to collect data sets and perform scientific experiments in order to have a better understanding about Earth, planets, or solar system or universe in general. Right hand side, you could see some of the examples of earthbound observation or moon, Mars, or galaxies, etc., or sun, by various scientific instruments or payloads. And the primary benefit of these payloads are basically they allow us to collect data and perform experiments in very harsh environments where otherwise human cannot reach there. It is almost inaccessible for humans to reach. And the categories of payloads I have listed down. They can be scientific payloads, communication payloads, navigation payloads, human support payloads, and cargo payloads. Scientific payloads, in a way, what we understand is on the spacecraft are generally telescopes, spectrometers, cameras, and various kind of radiometers and different types of probes. Communication payloads that last lecture would have been discussed, various transponders which are being used for communication purpose. Navigation payload, name itself tells the instruments which are used for understanding the navigation on Earth or on other planets or in the space. Human support payloads, the needs of humans in space, such as providing life support system, environment control, thermal control, waste management. So payloads related to that. Or lastly, the cargo payloads, which are used to transport the supplies, various parts of scientific instruments and equipments to the space station. So these are the general discussions about various payloads. But what we are going to discuss are about the payloads for space exploration. All of us, we know the space era started with Russia's Sputnik 1 in 1957, and it has been now more than 60, 70 years. And we have come a large path ahead after that particular great achievement. And to develop and design space instrument for a spacecraft which can work in very difficult and harsh space environment seems quite exciting, but it is at the same time, it is very, very challenging and difficult to develop some of those things. So as these kind of space instruments need to be developed, which are quite important for our exploratory study, they go through various stages of development, starting from a design on a paper, functional design, to an instrument in lab, and then in that instrument has to be proven with respect to its performance, and which ultimately goes after various developmental cycle for a finished mission. So what are the major stages of development of space instrument launch and operation? As you could see, there are various kinds of instruments. They are being built, designed and built by various teams of engineers and scientists at various institutes, depending upon its application and scientific utility. And they are being developed, tested before its launch. These kind of instruments or payloads, they can be integrated in the spacecraft. This is an integration on the spacecraft deck. The payload is being integrated, and ultimately they will be integrated into the rocket launcher. That means launch vehicle. On the top of this heat shield, the particular payload is being integrated, and after a various kind of testing and various kind of rigorous evaluation, once it is qualified, then it is ready for launch. It gets into the space by various kind of launcher, and after the launcher launches this payload in the space, these payload which is being developed by specific team of scientists or engineers, they will be actually operating it through their operating laboratories, how to operate, how to use those scientific instruments for a specific purpose. Okay, so for what we generally want to understand, what kind of themes we would like to explore in terms of space science and exploration. So there are generally there are many themes, but we can right now briefly tell astronomy and cosmology is one theme, planetary science is the second one, and heliophysics is third one. Astronomy or cosmology is the theme which studies the objects and phenomena beyond Earth, whereas the cosmology is study of origin of universe and its understanding about its evolution. Planetary sciences, it's a study of planets. We know various planets, including our own planet Mother Earth, and various celestial bodies like moons, asteroids, comets, etc. And the third one, that is the heliophysics. Heliophysics is nothing but it is being used, this term is being used to understand the science of the sun or sun solar system connection. That is called a solar physics, or exploration, discovery, and understanding of Earth environment, space environment, that is related to space weather. Or there are various system science that unites all these phenomena in the region of cosmos influenced by a star like our sun, that is called heliosphere. So ultimately, we try to develop various instruments or payloads for understanding these kind of themes. What do we observe in universe? What kind of things we would like to observe? The first one is the electromagnetic radiation through remote sensing. That means without touching any object, you observe certain radiation through photometry. That means radiation and its distribution. Through spectroscopy, that means distribution of radiation as a function of frequency or wavelength. Or polarimetry, that means use of radiations, polarimetric observation or polarimetric signatures, understand the unique phenomena. Or you other than radiation, you observe particles which are being actually pumped by various phenomena, those charged particles, or neutrals like neutrinos or some neutral atoms. Or the third one is the gravitational waves, which are being actually the fluctuation in the space and time, which generally is being caused by various kind of or major mergers of two compact objects like black hole, or black hole neutron star. So once we would like to understand the universe, you can understand it either by radiation, particles, or by waves. And if you consider the wavelengths, if you observe certain object, wavelengths give us the information or various windows in different layers of the atmosphere or the target itself. So we would like to understand the phenomena in multi-wavelength from the space. So as we all know, this electromagnetic radiation within solar system, they have a great range starting from radio waves to the X-rays, gamma rays, depending upon their frequency and the wavelengths. And this electromagnetic radiation generally is being used either scattered radiation, emitted radiation, or transmitted, or scattered or absorbed or emitted radiation in these various kind of electromagnetic energy levels. That means the main focus or the messenger from any electromagnetic payload which can be used to observe universe is electromagnetic spectrum. So you can, as I mentioned earlier, you do imaging through intensity measurement, you do spectroscopy, that means spectral distribution, or you do polarimetry through polarization. And these major techniques of electromagnetic radiation, they have their own characteristics which can be useful, either various spatial resolution, spectral resolution, radiometric resolution, or spectral distribution across the wavelengths, or the hyperspectral, that means information hidden in various spectral lines that can be observed, or the scattering and polarimetric properties for polarimetric observation. So one of the major examples one can see, which has changed the understanding of human being, is use of this Hubble or James Webb kind of telescope, which gives us various imaging in various observational windows of various wavelength bands, and it provides information about different structures, shape, size, and many times the texture also. And they can be they can be used for beautiful remote sensing purposes to understand space exploration studies. Why we want to do these multi-wavelength observations? As we said, see, this is the observation of same object, sun, at various wavelength regions. Either it is from 4500 angstrom to 1600 angstrom, 304 angstrom, and so on. You see the change of details or the power of multi-wavelength observations, which gives us detailed information about atmosphere of the sun, various layers of the sun, details of various phenomena depending upon the characteristics or the spectroscopy of the physics underlying some of these processes. These processes, they give, depending upon various physics laws, it gives the emission in various wavelength regions, and you can probe many observational characteristics. One of the examples which you would have heard is during May 2024, recently, very recently, the sun emitted a very strong solar flare, which is the largest in the solar cycle number 25, where a great explosion or storm has occurred with the number somewhere around classified as X 8.7, where X denotes the one of the most intense flare, classified as the brightest of that class, and 8.7 denotes the great strength of those solar flare. And you could see at various wavelength ranges how those solar flares, they give us different kind of observation or specific observation as a function of wavelength. So one can use these multi-wavelength observation for solar storm of things, or you observe it for multi-wavelength observation ranging from radio frequencies to gamma rays. One of the fields you can, in the space, you can see how from radio to gamma rays, they offer us unique features in this particular field. So understanding the formation and evolution of stars, galaxy and universe over cosmological time scale are the very obviously the prime goal of astronomical research. And universe generally presents a wide range of extreme environments, from very cold to very hot kind of objects, and which can be probed in varying frequencies, starting from, as I said, radio to gamma range spectral region. So you see some of the features which are quite prominent in one wavelength regions are not prominent in other regions, but some of the major clumps, one of the major features which are quite evident in other wavelength regions are not available in other spectral regions. So but likewise you can observe various kind of objects in astrophysics or astronomy or planetary sciences and get detailed information about the matter, dust, radiation and the atmosphere beneath those objects. The second one is this spectroscopy, how radiation is distributed as a function of wavelengths or frequencies. And if it is a continuous spectrum, visible spectrum, that is fine. But there are certain specific lines which are specific to an element like sodium, hydrogen, calcium, mercury, etc. So if you understand its absorption features or emission features, one can say that one spectra has sodium, other spectra has hydrogen, and so on. And they are typically, spectroscopy has a continuum emissions or line emission, generally governed by various physics-based laws of black body radiation law, Bremsstrahlung, or emissions in terms of absorption and emission lines. So quickly, we'll go through beautiful and one of the most important black body radiation laws, or two black body radiation law. One is called Planck distribution law, which describes, Planck has described this law, which says that as a function of wavelength and temperature, how various objects with high temperature to low temperature will have a spectral distribution of the energy. For example, you have this particular equation which Max Planck has given, which is nothing but a distribution of energy as a function of temperature and wavelength. So for example, if you have Earth with assumption of average temperature somewhere around, let us say, 290 to 300 Kelvin, it will have its distribution like this particular curve. If temperature is higher of 500 Kelvin, it will have this envelope. If it has more temperature, this envelope is progressing towards low wavelength region. And if the temperature is somewhere around average temperature of sun, let us say 6000 Kelvin, the Planck distribution shows the beautiful envelope of that particular energy. So now we have a temperature distribution or energy distribution or radiance distribution explained by Planck, which is unique in physics, but the peak of the wavelength, if you see somewhere, this 300 corresponds to 9.7, 9.8 micrometer, this 500 at lower wavelength, and ultimately, let us say 6,000 Kelvin corresponds to a wavelength peak. It's somewhere around 0.5 micrometer, and the shift of these peak is captured or denoted by an function or a law called Wien's displacement law, which is I have shown here. This is the one of the beautiful manifestation of black body radiation law. So if we want to understand low temperature, you have to observe these, and if you want to understand high temperature, you have to go beyond these wavelengths. This critical information about the how my instrument or payload is to be designed. These physics, simple physics helps us understanding what kind of payload I have to design. As I said, if I want to understand the Earth atmosphere, which is somewhere around 250 to 320 Kelvin, I have to observe Earth in 7 to 11 or 12 micrometer region. If I have to observe the Mars which has a low temperature range of, let us say, 130, 140, 160 kilometer to 270, 280 kilometer, I have to design my camera or thermal camera somewhere around 14, 15 micrometer temperature. Or if I want to understand the Venus, which is quite hot, I have to design my payload accordingly on lower wavelengths. So these are the fundamental laws which govern the design of instruments. One of very important discoveries in the history of space science has been this measurement of cosmic micro radiation, background radiation measurement, CMBR, designed by Dr. George Smoot and John Mather. What they did, they had an understanding, and physicists had said that the remnant of the originally explosion of the universe will have a equivalent temperature across universe somewhere around 3 to 4 Kelvin. And how to measure that kind of 3 to 4 Kelvin kind of object or that kind of radiation. So Professor Mather and Dr. Smoot designed this instrument called FIRAS, which has a beautiful sensitivity. That payload had a sensitivity which can work for very cold temperature around 3 Kelvin. And they measured this particular black body radiation curve and proved that CMBR exists somewhere with the temperature range of 2.7 Kelvin or approximately 3 Kelvin with a millimeter wavelength region. So this particular discovery or this payload observation or experiments, they'll earn through this particular observation, they earned 2006 physics Nobel Prize for establishing, for designing the instrument called COBE, that means Cosmic Background Explorer, and for their discovery of the black body form and isotropy in terms of anisotropy of cosmic micro background radiation. Then there are instruments of kind of Hubble Space Telescope. As I said, it has revolutionized the understanding of the space or universe through three kind of instruments: cameras, spectrographs, and interferometers. So what these spectrographs they do? They spectrograph, basically they depend upon the physics of spectroscopy, which actually breaks down, the instrument breaks down the various wavelength regions and various components, so that you can understand various elemental abundances or element or existing in any of these kind of observations. So one of the things are the spectrographs. The other one is telescope, that is called Hubble's Space Telescope Imaging Spectrograph, which also observes the spectrum, which basically reveals the various kind of elements which are available in various objects in the space. After Hubble actually was earlier technology, which was also one of the great kinds. The second one was the James Webb Space Telescope, but they call JWST, which is basically has got a capability 5 to 6 times that of the Hubble, and with its 18 hexagonal mirror segments with the gold-plated beryllium, which basically gives us a 21-foot mirror, design, with compared to 7-foot design of Hubble. It gives a great, platform for collecting, large kind of light. It gives you better or larger area for collecting, as I said, 6 times that of Hubble. And this particular instrument consisted of mid-infrared. It consists of mid-infrared instrument. That means it works in 3 micron to 20 micron kind of thing. Near infrared, that is 0.9 or 1 micron to 3 to 4 micron. Near infrared, that is somewhere around 0.7 onwards to 1 micrometer. And this kind of, it gives you beautiful beautiful combination of instrument at various wavelength regions. And the recent ones, which is actually the other than JWST, the observation of some of the proxy of black hole, which is called EHT, that means Event Horizon Telescope, the boundary of the space, in space around a black hole, which we call as an event horizon. And using this EHT configuration, that is a large telescopic or large configuration, one measures, scientists obtain an image of black hole at the center of galaxy M87, and which basically outlines the emission of very hot gas swirling around under the influence of strong gravity near its event horizon. And this M87 star or M87 is the supermassive object in the center of M87 galaxy. And the EHT, as I said, is a global array of telescope performing observation using the technique called very long baseline interferometry, that is called VLBI. So I'm not going into detail, just want to give you flavor of various wavelength and its capability. How some of the discoveries have been measured in the space exploration using electromagnetic radiation observation, working in various wavelength region. As I said, polarimetry, earlier I said polarimetry has its own capability. It gives us information about scattering, which is being actually induced by polarization and emission mechanism. And typically, basically, it actually has a unique power of explaining or probing some of unique features which is otherwise not possible through intensity measurement. And this image basically combines data from IXP, the X-ray observation, polarimetric observation. Left-hand side, the blue one is Chandra simple X-ray image, and right-hand side is IXP, where you could see, some features which are being observed through X-ray polarimetry over a supernova remnant Cassiopeia A object. And this line, basically the graphics, they show the IXP polarization measurement and which actually depicts the direction of the magnetic field across this region of remnant from this supernovae. So these unique feature can be observed only through polarimetry. Now we discussed what kind of electromagnetic radiation observations at various wavelength regions can be shown. Some major ones we saw. Now through particles, what kind of observation one can have? That is, the solar wind and particles within solar system through particle analyzer or direct detection of particles, which are basically created by various processes of solar wind or CMEs or some of the other atmospheric processes. And they are either charged or they are neutral in nature. And we try to understand this through mass spectrometry, the what kind of temperature it has, what kind of mass, charge, velocity distribution it has. So particles can be observed through some of these kind of systems. The other one is the gravitational waves, where people say that these are the ripples in the space-time caused by one of the most violent and energetic processes in the universe, as Albert Einstein, great Einstein, had predicted in around 1916 in his general theory of relativity, that massive accelerating objects would disrupt space-time in such a way that waves of undulating space-time basically would propagate in all direction away from the source. And these cosmic ripples, they travel at the speed of light, carrying basically information about their origin of their sources. So these gravitational waves, people use it uh, with various experiments. The latest ones are in are being done through some of the experiments, because these measurements are quite feeble in nature. These measurements have to be observed through a very highly sensitive interferometric measurement, which actually are being used. These are the one of the frontiers in the astronomy. And scientists, let us say for the example, they are proposing the laser interferometer in the space. That the one of the experiment is called LISA, the laser interferometer space antenna, which is a combination or constellation of 3 satellites to observe gravitational waves from the space with the great stability. Is kind of concepts are being promoted or proposed by NASA, ESA, and other laboratories to have a interferometric measurement of gravitational waves. Then one of the last sections, that means the remote sensing instruments and observations, what it can give us. Instruments I'll be quickly showing. They are working in different wavelength regions. Some of the examples we'll go through very quickly. One of the most and foremost from the India was the Mangalyaan mission, Mangalyaan 1, that means Mars orbiting mission 1. It had 5 instruments on board. One of the instruments or scientific payloads, what we called is Mars color camera, I have shown here, which was developed at Space Applications Center, Ahmedabad, and which gave us various kind of unique observation of Mars, which was a camera kind of RGB bare pattern camera of very smaller size and less resource hungry instrument. Because if you want to go through 6 to 7 crore kilometers in the space with very less resources, this was the one of the compact objects of 1.3 kilogram with very less power requirement of 3 watts. And it actually observed Mars, but before leaving Earth orbit, it gave us this beautiful image of Earth before going into the journey of 9 months to Mars. it actually captured Earth. Then on 24th of September 2014, when it actually reached the Mars, this is the first Mars image beamed or captured by MCC Mars Color camera on Mars Mangalyaan 1 mission. And this is the first image which was observed. Then systematically, it observed the global image of Mars, which gave us opportunity to understand larger phenomena in terms of dust devils. The you could see quite a lot clear Mars, but as a function of time, it is being actually surrounded by Earth or polar vortex or polar phenomena, some phenomena occurring at two poles and various other things. Or beautiful large canyon, the large Martian canyon, which actually has a some kind of clouds or haze captured in it, or Martian clouds in Asia Mons region. This is one of the beautiful images MCC had given. Lot of science is being done or can be done through some of these observations. That was in visible region. Now we come to the near infrared or thermal infrared region. So Mars mission had a camera or instrument called TIS, thermal imaging spectrometer, which measured the thermal emission from the Martian disk. Or as I said earlier, same principle is being used of thermal emission over JWST, which actually measures the radiation in infrared, near infrared and mid infrared and long or mid infrared spectral region, and which gives us information and formation about star and galaxy and other cosmic structures by basically analyzing the absorption and emission lines. Okay. Then if we go further, we have X-ray imagers, which are examples. There are a lot of examples. I have quoted one from India and other from outside. That is, one is in AstroSat of India, and other ones are from RACI, NASA. And this kind of X-ray imagers, they observe the high energy phenomena. Basically, they are occurring through or they occur or solar flares. Let us say soft X-ray region where solar flares with very observation can be done in this solar X-ray or then hard X-ray or some of the gamma ray burst as well. So these kind of X-ray spectrometers, either it was in AstroSat or right now in Aditya L1, where we have a Solexis, and this one is soft and other is hard X-ray imaging or measuring X-ray spectrometers, where you understand the basically high temperature plasmas, or you understand the elemental composition of some of those solar flares. What kind of composition those kind of solar flare has, and they actually govern the churning of the plasma, which are basically responsible for very, very high temperature region where from surface to its corona or atmosphere, which generally ranges from few thousand degrees Kelvin to millions of Kelvin. What kind of elemental composition it has, those kind of observations can be done through this kind of X-ray spectrometer. Or some of the ultraviolet regions, that is called UV imaging or UV spectrometers, which basically provides us information about some of other surface or layers, that is the coronal processes or chromospheric processes. Through these kind of observation you can have this as a spectral lines that can be used to characterize hot plasma, and it provides you stellar atmospheric information, study of galaxy, quasars and other cosmic entities. And example is AstroSat UVIT, or in Cassini UIIS of NASA. So this kind of imaging and spectrometers are used. The other one instruments which is working in the UV or visible ranges as a coronagraph, Aditya L1 has, which gives us the corona information, the information about the bright objects and basically the faint region surrounding the bright objects, which cannot be directly seen. It can be seen through instrument called coronagraphs. This can be used for sun as we are using for Aditya L1, or from some other stars also. So I'm not going into detail. There are a lot of this kind of coronagraph information available, either it from India or from outside India. This is one of the beautiful instrument was there, or SOHO LASCO from NASA as well. Or last section is on in situ observations. That means you observe certain phenomena or parameter through almost touching those so-called objects, or those parameters like magnetic strength, its direction and wavelength through magnetometers, or this magnetometer, either it is from India or some other paper, or some plasma observation through Langmuir probe kind of thing, where it measures the plasma potential, electron temperature, electron density, or energy distribution, electron energy distribution. Basically, this kind of observations, this kind of probe provides us information about the hot plasma or ionosphere in any planetary body. And this kind of observation, they are called in situ observation. One of the one of the missions in future India is planning, ISRO is planning, is Disha. There were many observational, Langmuir probes there in India or in, globally available. One can study that particular thing. Or some of the instrument called retarding potential analyzer or particle analyzer, basically they derive or they measure the energy of charged particle using, electrodes or series of electrodes to create a retarding potential. And basically they provide us observation through voltage observation. And some of these instruments, they are challenging in design, but it provides beautiful information about origin of various kind of solar wind protons, or variation of various alpha proton ratios and so on. One can have the understanding of energetic particles from solar flare and other activities as well. So there are various kind of analyzers and particle analyzers are available. Mass spectrometers, basically they provide you the mass to charge ratio in the neutral particles, and they provide us a understanding or measurement of composition, a neutral composition of any planet. Like there was an instrument from Space Physics Laboratory, SPL ISRO, called MANCA, which had this Mars exospheric neutral composition analyzer, which can give you the Mars to charge ratio of the particles in the Martian atmosphere. And last but not the least, I will show you 3 to 4 stages of how space instrument is being designed in laboratories. What kind of components go into that? What kind of steps go into the design of space instrument or scientific payloads? If you see, you have an object. From object, you have a radiation which has to be captured through optics. This optics, basically the optics, along with its lens and other assembly, they capture it on some device. And this device called detector or charge coupled device or any kind of device, they convert this electromagnetic radiation into the electrical signal. They work as a transducer and they convert this energy or electromagnetic radiation into the electrical signal, and then these electrical signals, they are being actually read out to electronics. So you have optics, you have detectors, you have electronics, and you have to have house, that means mechanical structure, which gives you a stability and house to that. So any electro or imaging instrument has to have light collection and focusing optics, detection system, electronics, and mechanical assembly. And mechanical assemblies, with for any space-based instrument, you have to have low mass and other low resource constraints. So it has to have beautifully designed mechanical structure with specific kind of stiffness, sensitivity, and material characteristics, and ultimately it has to have a light weight. Then you can have optics, either it is reflective, refractive, or catadioptic optic kind of system, where you have to have different kind of lens assembly. You have to have prisms, you have to have various kind of optical components which can be used either for reflective, refractive kind of systems, or ultimately you have to read out all the signals, as I said, through certain electronics. And this electronics, you have to have various kind of uh, analog to digital conversion, and have to have spacecraft telemetry, telecommand, temperature control, data handling. It has to have all those components other than the readouts. So, and you have to have detectors. Various kind of detectors are there. I'm not going into details, but you have to have detectors sensitive to various wavelength regions or various kind of radiations. And in the summary, what we discussed in our lecture is you have to have a specific instrument, that is called a space-based payload, to be designed based upon the scientific need, based upon the requirement of scientists or their teams. Once you develop those instruments, you put it in the spacecraft, put on this particular deck. Ultimately, it goes into this. I'm reiterating that, and it is being put in the launch vehicle. Ultimately, it goes into space. It is being parked at particular orbit, specific orbit in the space, and that instrument is being then controlled, used for specific scientific purposes through certain viewing geometry and required exposure levels. And those signals are being used. For development of algorithm which converts those numbers, scientific numbers, in specific products to be used, and which generally ultimately improves the scientific understanding, which can lead to discoveries in the space exploration. So the last but not the least, what I would like to say, because you have to have a mission which is very delicate in nature, which has to have very low mass resources, but it has to have a cutting edge, has to use cutting edge technology, one of the best hardware, one of the best technologies to be used. So what Robert Gold said, that the difference between an affordable and scientifically sound mission and no mission whatsoever is basically, it rests almost entirely, depends on the recent advanced instrument development. That means a country or a community has to have knowledge of advanced instrumentation to realize one of the base system in the space exploration. So with this, I thank you, all the participants and listener to this particular talk. I thank Chairman ISRO, Director Space Application Center, Director IIRS, Director SPO, Dr. Praveen Kumar, all the participants, IIRS team, my team members, specifically Mr. Manish Chauhan and Asif Mohammad Mandyapuram for this particular presentation, help me in making this presentation, and all the sites and internet material which is being used from ISRO, NASA, and ESA sites. Thank you.